The universe is governed by rules that make no sense. Black holes swallow light, and particles communicate instantly across vast distances, forcing scientists to tear up the old textbooks. By the end of this journey, you will understand 25 astonishing events that completely reshaped the laws of nature. We will explore how the echo of creation itself was discovered by accident and why tiny particles can be in two places at once. What single discovery do you think most challenged our idea of reality? That faint static hiss was the oldest song in the universe. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were calibrating a giant horn antenna in New Jersey, but they could not eliminate a persistent, maddening noise. It came from every direction in the sky, a constant microwave whisper they could not explain. They even scrubbed the antenna clean, suspecting the interference was caused by pigeon droppings. Yet the noise remained. This annoying background static was not a technical flaw. It was the cosmic microwave background radiation, the cooled and stretched remnant of the universe's fiery birth. This was the first tangible proof of the Big Bang, the afterglow from a time when the cosmos was just 380,000 years old, a hot, dense plasma finally cool enough for light to travel freely. Mapping this radiation gave us a baby picture of the universe, revealing tiny temperature differences that were the seeds for everything we see today, every galaxy, star, and planet. This discovery confirmed the universe was not eternal and static, but had a definite beginning and has been expanding ever since. It completely rewrote our story of cosmic origins, proving the laws of nature had a starting point. But if the Big Bang showed us how it all began, what happens when matter collapses into a point of infinite density, where the laws of physics as we know them simply break down? Einstein's spacetime fabric was not just a static stage, it could ripple. Picture two black holes, each with the mass of dozens of suns, locked in a final, frantic dance. As they spiraled inward and collided over 1 billion light-years away, they shook the universe, sending vibrations racing through the cosmos at the speed of light. For a century, these gravitational waves were just a mathematical prediction from Einstein's theory of general relativity, distortions in the fabric of reality so faint that Einstein himself doubted we could ever detect them. But in 2015, an observatory called LIGO proved him wrong. Its lasers measured a wobble in its long arms smaller than 1/10,000th the width of a proton, capturing the specific chirp of spacetime itself ringing from that ancient collision. Nobel laureate Kip Thorne described this moment as hearing the universe for the very first time. Until then, astronomy was almost entirely based on light, from radio waves to gamma rays. But gravitational waves are a completely different messenger, allowing us to perceive cosmic cataclysms that are completely dark to traditional telescopes. This single detection confirmed general relativity under the most extreme conditions imaginable and launched an entirely new field of science, gravitational wave astronomy. We can now listen to the invisible, from the violent mergers of neutron stars to the faint echoes of the Big Bang. It revealed that the cosmos is constantly humming with these subtle vibrations, a symphony of spacetime played by the most massive objects in existence. If we can now hear the fabric of the universe twisting, what happens when we observe the smallest building blocks of that same fabric, where the rules become even more bizarre? Einstein was deeply unsettled by the implications of his own work, calling one of its strangest consequences spooky action at a distance. This is the bizarre world of quantum entanglement. Picture two particles created together like a pair of cosmic twins. They become inextricably linked, sharing a single quantum identity. If you separate them, sending one to the far side of the galaxy, that connection remains. The moment you measure a property of one particle, such as its spin, the other particle instantly adopts the corresponding state. This happens immediately, seemingly faster than the speed of light. For decades, this was a philosophical debate, a troubling puzzle in the equations. Einstein believed this spooky action proved quantum mechanics was incomplete, that there must be hidden variables we did not yet understand. Then, in the 1980s, a series of brilliant experiments led by physicist Elaine Aspect put this idea to the test. Using a theoretical framework developed by John Bell, Aspect's team created pairs of entangled photons and measured their properties from opposite sides of a lab. The results were unequivocal. The particles were correlated in a way that no local hidden variable theory could ever explain. Measuring one photon did indeed force its twin into a specific state, an instantaneous connection that defied any classical notion of distance and locality. This does not allow us to send messages faster than light, as the outcome of each measurement is random, but it does reveal a profound and fundamental interconnectedness in the fabric of reality. The universe, at its most basic level, is not a collection of separate objects but a woven tapestry where particles can share a connection that transcends space itself. This quantum weirdness is not just a laboratory curiosity. It is the foundational principle behind emerging technologies like quantum computing, which promises to solve problems impossible for today's supercomputers, and quantum cryptography, which could create truly unbreakable codes. It hints that our everyday experience of a local, cause and effect world is only a surface layer over a much stranger, deeply interconnected reality. But if this spooky connection governs the tiny quantum world, what happens when these bizarre rules manifest in objects large enough to see with our own eyes? A single electron fired toward a barrier with two narrow slits should logically pass through one or the other. Logic, however, has little authority in the quantum realm. When no one is watching, the electron does not choose a path. Instead, it behaves as if it is a spread-out wave, passing through both slits simultaneously and interfering with itself on the other side. This creates a stripy pattern on the detection screen, a signature of overlapping waves, not a single particle's impact. The act of observation shatters this ethereal state. The moment a scientist sets up a device to see which slit the electron uses, the wave-like behavior vanishes. The electron arrives at the screen as a definite particle, having traveled only one path, and the beautiful interference pattern is erased. This is the profound paradox of the double-slit experiment. It reveals that an electron, and indeed all fundamental particles, are neither pure particles nor pure waves. They are something far more nebulous, existing in a blurry cloud of possible states, a superposition of all possible paths and positions, until the act of measurement forces them to pick one. This is the core of wave-particle duality, the bizarre idea that what something is depends entirely on whether you are looking at it. The physicist Richard Feynman argued this single phenomenon contains the only true mystery of quantum mechanics. To make this abstract concept more tangible, Erwin Schrödinger proposed his famous, if unsettling, thought experiment. He asked us to imagine a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and the cat dies. If it does not, the cat lives. According to quantum rules, until the box is opened and observed, the atom exists in a superposition of both decayed and not decayed states. Consequently, the cat is proposed to be both alive and dead, a grotesque but logical extension of the superposition we see in the double-slit experiment. This was not a proposal about feline mortality. but a stark illustration of how absurd the quantum world seems when scaled up to our everyday reality. The implications ripple far beyond philosophical puzzles. This very principle is the engine behind the electron microscope, which uses the wave nature of electrons to see details far smaller than light could ever reveal. It is the foundation for the quantum computers now being built, which rely on qubits existing in superposition to perform vast calculations in parallel. This single experiment forces a monumental reconsideration of existence itself, suggesting that at its most fundamental level, reality is not a collection of definite things, but a sea of probabilities waiting to be crystallized by a conscious observation. If our very gaze can collapse a wave of possibility into a solid fact, how much can we ever truly know about the quantum world's frantic, hidden dance? This fundamental fuzziness is woven into the universe itself. Werner Heisenberg's uncertainty principle reveals a startling limit to what we can know. It states that certain pairs of properties, like a particle's position and its momentum, are locked in a cosmic tug of war. The more precisely you pin down its location, the less you can possibly know about where it is going and how fast. This is not a flaw in our microscopes or a lack of human ingenuity. It is a fundamental rule of reality, a direct consequence of the wave-like nature of all quantum objects. Imagine trying to get a perfect, still photograph of a hummingbird in a pitch-black room. You could flash a brilliant, instantaneous light to freeze its position with perfect clarity, but in that single, blinding moment, you would be completely unable to determine its speed or direction. The very act of seeing its location destroys your ability to measure its motion. This is the essence of the uncertainty principle. At the quantum level, the universe is not a clockwork mechanism where every future state can be predicted from the present. It is a realm of inherent probability and chance, a direct challenge to the classical, deterministic view of a predictable cosmos. This has profound philosophical ripples, suggesting that a perfectly knowable, objective reality may be an illusion, and that the observer is always, in some small way, a participant. How does this fundamental uncertainty escape the tiny quantum world and shape the cosmos on the grandest scales? It plays out in the terrifying emptiness of space, where a relentless tug of war occurs at the boundary of reality itself, a place from which nothing, not even light, was ever supposed to escape. The event horizon is a boundary in space where the escape velocity equals the speed of light, a one-way door from which nothing can return. This is the defining feature of a black hole, a cosmic prediction born from Einstein's theory of general relativity. While their existence was confirmed indirectly in the 1970s by observing stars whipping around an invisible, massive companion, their true nature remained shrouded in mystery. At the very heart of a black hole lies the singularity, a point where all the collapsed matter is compressed into infinite density, and the known laws of physics simply cease to apply. It is a place where space and time as we understand them come to an end. For a long time, it was believed that nothing, not a single shred of information, could ever escape a black hole's gravitational grip. Then Stephen Hawking made a revolutionary calculation. He realized that if you brought quantum mechanics into the picture, the intense gravity at the event horizon could spontaneously create pairs of particles. In a fleeting quantum event, one particle falls into the black hole while the other escapes, radiating away into space. This Hawking radiation means black holes are not eternally stable. Over unimaginable eons, they slowly leak energy and evaporate, posing a profound puzzle about the ultimate fate of anything that falls inside. For decades, these objects were only understood through mathematics and indirect evidence. That changed in April 2019, when the Event Horizon Telescope collaboration released the first ever direct image. This was not a picture of the black hole itself, which is invisible, but of its shadow, a dark silhouette set against the brilliant, swirling glow of its superheated accretion disk. The image confirmed the dramatic bending of light around the event horizon, a perfect ring of fire known as the photon ring, showing us the violent chaos that surrounds the ultimate calm. Near this boundary, gravity warps spacetime so severely that time itself appears to slow to a crawl from an outside perspective. An object falling in would seem to freeze at the horizon, its light red shifting into oblivion, while from its own perspective, it would cross that threshold and be torn apart by tidal forces. Black holes are the ultimate laboratories, forcing the two great pillars of modern physics, general relativity and quantum mechanics, to confront each other in the most extreme environment imaginable. We have already heard what happens when these monsters collide. The gravitational wave chirps that signal a violent merger. But if black holes represent the pinnacle of gravitational collapse, a different and equally puzzling discovery was happening on the grandest scale of all, a finding that would reveal the universe is not just expanding, but flying apart faster and faster. For centuries, astronomers assumed the cosmic expansion was slowing down, that the collective gravity of all matter was acting as a cosmic brake on the Big Bang's initial momentum. The great question was whether this gravitational pull was strong enough to one day reverse the expansion into a big crunch, or if the universe would simply coast onward forever, gradually slowing. The answer, when it came, was neither. In 1998, two independent teams of researchers were observing a specific kind of stellar explosion, a Type 1, a supernova, which acts as a standard candle for measuring vast cosmic distances. By comparing how bright these supernovae appeared with how much their light had stretched or red shifted, they could measure not just how fast the universe was expanding, but how that speed had changed over billions of years. The data pointed to a shocking conclusion. The most distant and therefore oldest supernovae were dimmer than expected. This meant they were farther away than anyone had predicted, which could only be true if the expansion of the universe had been slower in the past. The cosmos was not slowing down, it was speeding up. This discovery of an accelerating universe was so profound and counterintuitive that it earned the teams the Nobel Prize in Physics in 2011. It was as if you tossed a ball into the air, expecting it to fall back, only to watch it shoot away from you faster and faster into the sky. Something was overpowering gravity itself, a mysterious, repulsive force woven into the fabric of space. This something was named dark energy. We cannot see it, trap it, or even fully understand it, but we can measure its overwhelming influence. Dark energy constitutes roughly 68% of the entire mass energy content of the universe. It is the dominant component of reality, and its primary effect is to push galaxies apart from one another at an ever-increasing rate. The most straightforward explanation for dark energy is Einstein's cosmological constant, a kind of innate energy inherent to empty space itself. As the universe expands and more space comes into existence, more of this repulsive energy appears, driving the acceleration ever faster. Other theories suggest it might be a dynamic energy field that has changed over the lifetime of the cosmos. Whatever its true nature, its implications for the ultimate fate of the universe are staggering. The previous visions of a fiery big crunch or a gradual coasting have been replaced by the prospect of a big freeze or heat death. In this future, the acceleration continues unchecked, carrying galaxies away from each other so effectively that the observable universe shrinks. Eventually, star formation will cease, black holes will evaporate, and the cosmos will become a cold, dark, and ever more empty void, with isolated particles drifting infinitely apart. Dark energy redefined our cosmic inventory, showing that the familiar atoms making up stars, planets, and us, account for less than 5% of everything that exists. If this invisible energy drives the cosmos apart, what is the unseen force holding it all together? The ghostly scaffolding that prevents galaxies from simply flying apart as they spin. Galaxies spin at speeds that defy logic. The stars on their outer edges whip around so fast that the visible matter alone could never hold them together. They should tear themselves apart, scattering stars across the void. Yet they do not. Something invisible, a vast and unseen hand, holds them intact. This is the ghost in the cosmic machine, dark matter. Its story begins not with a sighting, but with an inference. In the 1930s, a sharp-witted astronomer named Fritz Zwicky was studying the Coma Cluster, a group of galaxies bound by gravity. He calculated the mass required to keep these galaxies from drifting away from each other and found a staggering discrepancy. The visible galaxies provided only a tiny fraction of the necessary gravitational glue. He called this missing mass Dunkel Materie, dark matter, a substance that did not interact with light in any way. For decades, this was a fringe idea, until the 1970s when Vera Rubin provided irrefutable evidence. She meticulously mapped the rotation speeds of stars within spiral galaxies, expecting them to slow down farther from the luminous center, just as planets in our solar system move more slowly the farther they are from the Sun. Instead, she found the speeds remained constant, a flat rotation curve that meant an enormous halo of invisible matter must be enveloping each galaxy, its gravity gripping the outer stars and whipping them around. We now know this dark matter makes up about 27% of the universe, nearly 6 times the amount of all the normal matter we can see. It forms an invisible scaffold, a cosmic skeleton upon which galaxies are built and around which they congregate in vast clusters and filaments. We can map its distribution through a phenomenon called gravitational lensing. The immense gravity of a dark matter concentration bends the fabric of space-time, acting like a giant lens that distorts and magnifies the light from galaxies behind it. By studying these stretched and warped images, we can trace the outline of the invisible mass that caused the distortion. So what is it made of? It is not made of atoms. It does not consist of protons, neutrons, or electrons. It is something entirely new, a particle beyond the standard model of physics. The leading candidates are WIMP, or weakly interacting massive particles, which would be heavy and interact only through gravity and the weak nuclear force. Another possibility is the action, an extremely light particle predicted to solve other puzzles in particle theory. For decades, scientists have been hunting for these phantom particles. Deep underground, in mines shielded from cosmic rays, detectors wait for the rare ping of a dark matter particle bumping into a normal atom. In giant particle colliders like the Large Hadron Collider, physicists try to create dark matter in high-energy collisions, hoping to spot its missing energy. So far, it has remained stubbornly elusive. Its existence is one of the most profound embarrassments in modern science. We know it shapes the entire cosmos, that it guided the formation of every galaxy and cluster we see, yet we have no idea what it is. It is a fundamental component of reality that is completely hidden from our senses and our finest instruments, a constant reminder of how much of the universe remains in shadow. This invisible architecture holds the galaxies together, but how do we begin to map a ghost? We use the very fabric it warps, turning the universe itself into a lens to reveal its deepest secrets. Light itself can be bent by the weight of the cosmos. A massive object like a galaxy cluster warps the fabric of space-time around it so profoundly that it acts like a giant lens, distorting and magnifying the light from galaxies that lie far behind it. This is gravitational lensing, a dramatic confirmation of Einstein's theory of general relativity. We first saw this cosmic mirage during the solar eclipse of 1919, when stars near the Sun appeared slightly out of place, their light subtly curved by the Sun's gravity. Today, this effect is one of astronomy's most powerful tools. It can stretch a distant galaxy into a long, luminous arc, or, if the alignment is perfect, create a complete Einstein ring, a halo of light encircling the foreground mass. But its true power lies in revealing the invisible. When we see multiple, distorted images of a single galaxy, we are essentially mapping the distribution of dark matter, the unseen mass responsible for the lensing effect. This natural telescope also allows us to peer deeper into the universe than ever before. It can amplify the faint glow of the most distant galaxies, letting us study the first generations of stars. It has even been used to detect exoplanets by spotting the temporary brightening caused when their gravity focuses the light of a background star. Gravitational lensing turns the entire universe into a vast optical instrument, using the very warp of reality to uncover secrets from the cosmic dawn. What other relics from the first moments of time can this natural telescope reveal? Our next event peers back to the very beginning. The universe underwent a growth spurt so violent it defies common sense. In the very first fraction of a second, a speck of reality smaller than a single atom ballooned to the size of a galaxy cluster, expanding faster than the speed of light itself. This was cosmic inflation, a concept proposed by physicist Alan Guth in the 1980s to solve profound puzzles left by the Big Bang. Why, for instance, is the cosmos so incredibly uniform? The ancient light from the cosmic microwave background shows the same temperature in all directions, yet these regions were too far apart to have ever been in contact if the universe had always expanded at its current rate. This is the horizon problem. Inflation solves it by suggesting that the entire observable universe was once a tiny, connected patch stretched to a colossal scale in an instant, smoothing out all wrinkles and temperature differences. It also explains why the geometry of our universe appears so perfectly flat, a delicate balance that standard Big Bang theory could not account for. But inflation did more than just iron out the cosmos. It also provided the seeds for all structure. The quantum fluctuations that flickered into existence during that frantic expansion were stretched to astronomical sizes. These tiny ripples in density became the gravitational anchors for everything that followed. The slightly denser spots pulled in more matter, eventually growing into the vast cosmic web of galaxies, clusters, and voids we observe today. We see the direct imprint of these primordial ripples in the subtle temperature variations of the cosmic microwave background, a fossilized map of the universe's first moment. While a smoking gun detection of the gravitational waves generated by inflation remains a major goal for future observatories, the theory's explanatory power has made it a cornerstone of modern cosmology. It redefined our origin story, revealing that the initial conditions for our entire cosmic history were set in a breathtakingly brief and explosive event. With a stage set by inflation, a smooth and rapidly expanding universe was ready for its next act, the forging of the very first elements from a seething primordial fire. The universe was a searing nuclear cauldron in its first few minutes. During that fleeting window, from just 1 second to about 20 minutes after the beginning, the entire cosmos functioned as a single, unimaginably dense fusion reactor. This was the era of Big Bang Nucleosynthesis, the fiery process that forged the very first atomic nuclei from a chaotic sea of protons and neutrons. As the universe expanded and cooled at a ferocious rate, these fundamental particles began to stick together. Pairs of protons and neutrons formed deuterium, and these deuterium nuclei then rapidly fused into helium. The frantic dance was governed by a precise balance between the universe's expansion rate and the strength of the nuclear forces. When the temperature dropped too low for fusion to continue, the process slammed to a halt. What it left behind was a cosmic ash of about 75% hydrogen and 25% helium by mass, with only the barest whisper of lithium. For decades, this was a theoretical prediction. Then, astronomers looked at the oldest stars in our galaxy, stellar fossils that formed before heavier elements were common. The chemical composition of these ancient stars matched the predicted abundances with stunning accuracy. This agreement was a monumental victory for the Big Bang model. It proved the universe was indeed once hot and dense enough for nuclear fusion to occur everywhere at once. Furthermore, the precise amount of helium and deuterium produced acts as a cosmic ledger, allowing scientists to calculate the density of ordinary matter in the early universe. This confirmed that the atoms making up everything we see, from stars to planets to ourselves, account for less than 5% of reality. So why did this cosmic forge stop after making just the lightest elements? The universe was simply expanding too fast. To build heavier nuclei like carbon or oxygen, you need a stable, dense environment where triple collisions can occur, but the density was plummeting too quickly. The nuclear fires were extinguished by the relentless expansion of space itself, leaving a universe filled with a pristine, simple gas of hydrogen and helium. The stage was now set, but the story of the elements was far from over. How did we get from this primordial simplicity to the rich chemical diversity essential for life? The answer would require a new kind of factory, one that would ignite inside the hearts of the first stars. The primordial universe held only the lightest elements, a simple soup of hydrogen and helium. But for planets and life to emerge, something had to forge the rest of the periodic table. That cosmic alchemy began when the first stars ignited. Deep within a star's core, a relentless battle rages. The immense gravity of the star's own mass crushes the core, creating unimaginable pressure and heat. This forces atomic nuclei, which naturally repel each other due to their positive charges, to slam together and fuse. In stars like our Sun, this process is a steady furnace, patiently welding hydrogen atoms into helium. For billions of years, this fusion provides the outward pressure that balances the inward pull of gravity, creating a stable, shining star. But the story changes dramatically for stars much more massive than our Sun. As they age and exhaust the hydrogen in their cores, the balance shifts. Gravity gains the upper hand, crushing the core further until it becomes hot and dense enough to ignite the next fuel. Helium atoms begin to fuse, creating carbon. Carbon then fuses into oxygen, and so on, building heavier elements in concentric shells like the layers of a cosmic onion. This chain of fusion continues, creating neon, magnesium, and silicon, all the way up to iron. Here, the process hits a wall. Fusing iron does not release energy, it consumes it. The star's central furnace suddenly sputters and dies. Without the outward push from fusion, there is nothing left to fight gravity. The core collapses in less than a second. This catastrophic implosion triggers a titanic rebound explosion, a supernova, that blasts the star's entire outer layers, now enriched with these newly forged elements, out into the galaxy. But the creation of the very heaviest elements like gold, platinum, and uranium requires an even more extreme environment. These are forged in the chaotic aftermath of a supernova or in the violent collisions of neutron stars through a process called rapid neutron capture. In these fleeting moments, a flood of neutrons bombards existing atomic nuclei, building them up into heavy, unstable elements almost instantly before they have a chance to decay. This stellar nucleosynthesis, a concept masterfully pieced together by Fred Hoyle and others in the 1950s, solved the mystery of our cosmic origins. It revealed that every atom of oxygen in our lungs, every carbon atom in our cells, and every particle of iron in our blood was once forged in the heart of a long-dead star. We are not just inhabitants of the universe, we are literally made of stardust, the recycled remains of these ancient stellar explosions. This profound connection between the life and death of stars and the chemical richness of our galaxy completely rewrote our place in the cosmos. What happens in the heart of that final, catastrophic collapse when a star's core is crushed into the universe's most bizarre state of matter? A star's final moments unleash more energy than our sun will produce in its entire 10 billion-year lifetime. In a matter of seconds, a supernova can outshine its entire host galaxy, a cosmic flash so brilliant it can be seen across the universe. The most famous recent example, Supernova 1987A, was a titanic detonation in the nearby Large Magellanic Cloud. For weeks, it was visible to the naked eye, a sudden, new point of light that captivated astronomers worldwide. Its light was not the only messenger. Hours before the visible explosion, detectors on Earth recorded a burst of neutrinos, nearly massless particles that had streamed directly from the collapsing stellar core, offering a direct glimpse into the heart of the catastrophe. These explosions arise from two primary paths. The first is the core collapse supernova, the fate of stars more than 8 times the mass of our Sun. When such a star exhausts its nuclear fuel, its core, now mostly iron, can no longer resist its own immense gravity. It collapses from a sphere the size of Earth down to a city-sized ball of neutrons in less than a second. The rebound from this unimaginable compression blasts the star's outer layers into space at nearly 1/10 the speed of light. The second path involves a white dwarf, the dense, Earth-sized remnant of a Sun-like star. If this white dwarf is in a binary system and siphons enough material from its companion, it can be pushed over a critical mass threshold. This triggers a runaway thermonuclear explosion that utterly obliterates the dwarf, leaving nothing behind. Beyond their spectacular light show, supernovae are the universe's ultimate element factories. The core collapse variety creates and scatters all the elements from oxygen to iron forged in the star's earlier life. But the real cosmic alchemy happens in the seconds following the collapse. In an environment flooded with neutrons, atomic nuclei can rapidly capture these particles, building up into the heaviest elements in the periodic table before they have a chance to decay. This rapid neutron capture process, or R process, is responsible for creating nearly half of all elements heavier than iron, including gold, platinum, and uranium. The gold in a wedding ring or the uranium in a power plant was forged in the violent death throes of a massive star. These explosions also serve as fundamental tools for cosmology. Type 1, a supernova, those stemming from white dwarf explosions, have a remarkably consistent peak brightness. This makes them perfect standard candles, allowing astronomers to gauge vast intergalactic distances. It was precisely this property that led to the shocking discovery of dark energy. By revealing that distant supernovae were fainter than expected, proof the universe's expansion is accelerating. The aftermath of a supernova is just as important as the blast itself. The expanding shock wave, rich with newly synthesized elements, slams into surrounding interstellar gas, compressing it and triggering the formation of new stars and planetary systems. The remnant itself, a cloud of glowing, tangled gas, can be studied across the entire electromagnetic spectrum. Radio telescopes trace the structure of the expanding shell. X-ray observatories see the multimillion-degree gas, and infrared instruments detect the warm dust. Each wavelength reveals a different chapter in the story of the explosion's interaction with its environment. These cosmic explosions seed galaxies with the chemical diversity necessary for rocky planets and, ultimately, life. But what remains after the dust begins to settle? The collapsed core of the star often survives, compressed into an object so dense that a single teaspoonful would weigh billions of tons, a pulsar. A city-sized object can spin hundreds of times every second, a blur of unimaginable density whirling in the void. These are pulsars, the cosmic lighthouses first detected in 1967 by Jocelyn Bell Burnell. Her radio telescope data revealed a signal so perfectly regular, ticking with metronomic precision, that it was briefly nicknamed LGM for Little Green Men, a half-serious consideration of an artificial source. The true explanation was just as astonishing. A pulsar is a neutron star, the collapsed core of a massive star that went supernova, now compressed into a sphere only about 12 miles across. In this state, matter is crushed beyond recognition. A single teaspoon of neutron star material would weigh billions of tons, the mass of a mountain packed into a tiny speck. As this incredibly dense sphere rotates, its powerful magnetic fields funnel radiation into narrow beams from its poles. If one of these beams sweeps across Earth, like the spinning lamp of a lighthouse, we observe a pulse of energy with every rotation. The discovery of pulsars opened a new window into the most extreme states of matter in the universe. They are nature's ultimate precision clocks, their pulses so reliable that astronomers use them to test the very fabric of spacetime. The most famous example is the Hulse-Taylor binary pulsar, discovered in 1974. This system consists of two neutron stars orbiting each other, one of them a pulsar. By meticulously tracking the timing of its pulses for decades, Russell Hulse and Joseph Taylor were able to show that the stars were slowly spiraling inward, losing energy in exact agreement with the predictions of Einstein's general relativity. They were losing that energy by radiating gravitational waves. This was the first indirect but brilliant confirmation that these ripples in spacetime were real, decades before LIGO made a direct detection. The ultimate fate of such a binary system is a spectacular collision. When two neutron stars finally merge, they create a cataclysm known as a kilonova. In 2017, gravitational wave observatories felt the spacetime shudder from such an event, while telescopes across the globe saw the corresponding flash of light. The analysis of that light revealed the signature of newly forged heavy elements, including vast amounts of gold and platinum. A single neutron star merger can create more gold than the mass of our entire planet, seeding the galaxy with the precious elements that later become part of new solar systems. Pulsars and neutron stars are the ultimate laboratories for physics, allowing us to probe the behavior of matter at densities impossible to recreate on Earth and to witness gravity operating at its most extreme. A microsecond after the Big Bang, the universe was a different kind of fire. The familiar protons and neutrons that make up our world had not yet formed. Instead, the cosmos was filled with a seething, primordial soup, a state of matter where the fundamental building blocks of atomic nuclei, quarks and gluons, roamed completely free. This is the Quark-Gluon Plasma, a fleeting phase of reality that existed when the temperature was over 1 trillion degrees. To understand our own origins, we had to find a way to recreate this ancient cosmic condition. The tool for this task is the particle collider. In machines like the Relativistic Heavy Ion Collider and the Large Hadron Collider, scientists do not just smash single protons. They accelerate entire heavy ions like gold or lead to over 99.999% of the speed of light and slam them together. The resulting collision, for a sliver of a second, concentrates an immense amount of energy into a tiny volume, melting the ions and creating a pinpoint fireball of Quark-Gluon Plasma. The behavior of this plasma was a major surprise. Instead of acting like a superheated gas, it flows with almost no internal friction. It is what physicists call a nearly perfect fluid. Imagine stirring a cup of this plasma with a spoon. It would offer less resistance than water, swirling and eddying with an almost eerie smoothness. This property reveals deep secrets about the strong nuclear force, the fundamental interaction that glues quarks together to form protons and neutrons. In our everyday world, this force is so powerful that quarks are permanently confined within particles. You can never isolate a single quark. The Quark-Gluon Plasma is the only state where this confinement is temporarily broken, allowing us to study the force in its unshielded, primordial form. By watching this droplet of the early universe expand and cool, we are witnessing the very moment it transitions back into the ordinary matter that would eventually build stars and planets. Each collision is a tiny, man-made Big Bang, allowing us to run the cosmic clock backwards and observe the fundamental forces of nature at their most extreme. How do we capture the evidence of a fireball that lasts less than the blink of an eye? Deep beneath the border of France and Switzerland lies a 27-kilometer ring of tunnels, a cathedral of science built to interrogate reality itself. This is the Large Hadron Collider, the world's most powerful particle accelerator. Its mission is breathtakingly simple and profound. It smashes protons together at velocities just a whisper shy of the speed of light, recreating, for a fleeting instant, the conditions of the universe when it was less than a trillionth of a second old. Within the debris of these microscopic fireballs, physicists sift for clues to the most fundamental questions. What are the basic building blocks of everything? Why does anything have mass at all? For decades, the cornerstone of this understanding was the Standard Model of particle physics, a brilliant but incomplete theory. It successfully described the menagerie of particles and 3 of the 4 fundamental forces, but it had a glaring hole. The theory demanded that particles like electrons should be massless, zipping through the cosmos at the speed of light. Yet we know they have mass, and without mass, atoms could not form, and the universe would be a featureless soup of radiation. Something had to be breaking the symmetry, something had to be giving particles their substance. That something was the Higgs field, an invisible energy field that permeates all of space. As particles move through this field, they interact with it, and that interaction is what we experience as mass. Some particles, like photons, glide through untouched and remain massless. Others, like the top quark, plow through and acquire significant mass, but a field is an abstract concept. To confirm its existence, science needed to find its corresponding particle, the Higgs boson. This was the primary quarry for the Large Hadron Collider. 2 massive detectors, ATLAS and CMS, stood ready to capture the evidence. They are essentially gigantic, 100 million pixel cameras, surrounding the collision points and recording the subatomic shrapnel. On July 4, 2012, the announcement came. Both collaborations had independently observed a new particle with the expected properties. The Higgs boson had been found. This was not just the discovery of another particle. It was the validation of a mechanism that explains the very structure of our material world. It completed the Standard Model, but it also opened new puzzles. The Higgs boson's own mass is curiously light, a fact that has theorists proposing new ideas like supersymmetry, which suggests every known particle has a heavier, unseen twin. The collider also hunts for the particles that might make up dark matter and even for evidence of extra-spatial dimensions hidden from our perception. Each collision is a voyage back to the universe's first moments, a direct test of the laws that govern everything from the smallest quark to the largest galaxy cluster. If we can recreate the primordial fire to understand why matter has substance, what cosmic accident explains why there is any matter here at all? The universe began with a perfect balance of matter and antimatter, a cosmic symmetry that should have been its own undoing. For every particle of matter created, an antiparticle was its mirror twin. When matter and antimatter meet, they annihilate in a flash of pure energy. According to this perfect ledger, every particle in the early cosmos should have found its antimatter counterpart, leading to total mutual destruction. The entire universe should have become a vast, empty sea of light, with not a single atom left behind to form galaxies, stars, or us. Yet here we are in a world made entirely of matter. Something broke the symmetry. That crucial crack in the cosmic mirror is known as CP violation. The letters C and P stand for charge and parity. Charge conjugation means swapping a particle with its antiparticle. Parity is like looking at the universe in a mirror, reversing left and right. For a long time, physicists assumed the laws of physics were symmetric under both these operations combined. A reaction involving particles should look identical to the mirror image reaction involving antiparticles. But in 1964, an experiment with neutral kaons, strange and ephemeral particles, proved this fundamental assumption wrong. Researchers James Cronin and Val Fitch found that the neutral kaon and its antimatter twin did not decay in exactly the same way. There was a tiny 1 in 1,000 difference in their behavior. This was not just a minor statistical fluke. It was a fundamental crack in the mirror of reality, a slight preference in the laws of physics for matter over antimatter. This discovery earned them the Nobel Prize and provided a crucial ingredient for explaining our existence. The great physicist Andrei Sakharov had already outlined the 3 conditions necessary for a matter-dominated universe to emerge from a symmetric beginning. The universe must be out of thermal equilibrium. It must involve interactions that violate the conservation of baryon number, which is essentially the tally of matter particles, and it must contain CP violation. The kaon experiment confirmed that third, vital piece. This CP violation is built into the standard model of particle physics, primarily through a complex mathematical matrix that describes how quarks mix and change. But there is a problem. The amount of CP violation we have measured so far is far too small to account for the overwhelming abundance of matter we see in the cosmos. It is like finding a single dropped coin when you need to explain a mountain of treasure. This discrepancy is a glaring sign that our current model is incomplete. The hunt is now on for additional sources of this symmetry breaking. Major experiments at the Large Hadron Collider, specifically the LHCb detector, are meticulously studying the decays of beauty quarks, searching for any deviation that might point to new physics. Meanwhile, enormous neutrino observatories like Super Kamiok and in Japan and the Deep Underground Neutrino Experiment in the United States are focused on a different ghostly particle. Neutrinos may hold the key. If neutrinos and antineutrinos behave differently, a phenomenon known as neutrino CP violation, it could provide the missing piece of the puzzle, explaining how a universe poised for perfect annihilation instead became a material world. This search redefines our quest for origins. It is no longer just about how the universe began, but why it is made of the stuff it is, and why there is something rather than nothing. The faint imbalance in a kaon decay hints at a deeper, hidden asymmetry woven into the fabric of the laws themselves. How do we search for an answer in the most elusive and mysterious particles of all, the neutrinos that flood the cosmos yet barely interact with anything? A ghostly particle can change its very identity mid-flight. These are neutrinos, the universe's most elusive and abundant particles with mass, capable of phantoming through light years of solid lead without a single interaction. For decades, physicists were baffled by a solar mystery. Theories predicted a specific number of electron neutrinos should be streaming from the Sun's core, the site of its nuclear fusion. Yet detectors on Earth consistently counted only about a third of that expected number. Where were the missing neutrinos? The answer was not that they were missing, but that they were in disguise. A neutrino is not a single, static entity. It exists in a quantum superposition of three types, or flavors: electron, muon, and tau. As a neutrino travels through space, it perpetually oscillates between these three identities. An electron neutrino born in the Sun's heart might become a muon neutrino by the time it reaches Earth, and then a tau neutrino moments later. Our detectors, tuned to catch only electron neutrinos, were blind to the neutrinos that had transformed during their journey. This phenomenon, neutrino oscillation, was definitively confirmed by the Super-Kamiok and Sudbury neutrino observatory experiments in the late 1990s and early 2000s. The profound implication is that neutrinos must have mass. A massless particle traveling at the speed of light would experience no time and could not change. The very fact that they oscillate proves they have a tiny but non-zero mass. This single discovery shattered a foundational pillar of the original standard model of particle physics, which had assumed for decades that neutrinos were massless. It was an undeniable sign that our most complete theory of the fundamental world is incomplete. The quest to understand this tiny mass now points toward new, grander theories, such as the seesaw mechanism, which suggests the existence of incredibly heavy, sterile neutrinos that would balance the scales and explain why our known neutrinos are so inexplicably light. Beyond rewriting textbooks, these chameleon particles are crucial cosmic messengers. The burst of neutrinos that arrived from supernova 1987A, hours before the light, confirmed our models of stellar core collapse. Gigantic detectors like IceCube, with thousands of optical sensors buried deep in the Antarctic ice, now use the entire planet as a shield to catch the rare, high-energy neutrinos that scream across intergalactic space, pointing back to their violent origins like supermassive black holes. Perhaps most importantly, the study of neutrino oscillations is the front line in the search for the ultimate source of cosmic asymmetry. If neutrinos and antineutrinos oscillate at different rates, it would constitute a major new source of CP violation, potentially providing the final piece to the puzzle of why the universe is made of matter. These ghostly shape-shifters, once thought to be mere spectators, are now central characters in the story of cosmic evolution, their silent dance influencing the very fate of the cosmos. A dying star broadcasts its final moments not in light, but in ghostly particles. When the core of a massive star collapses, the resulting supernova unleashes a cataclysm where 99% of the total energy is not released as light, but is carried away by a tremendous flood of neutrinos. These particles stream outward almost at the speed of light, hours before the shockwave even reaches the star's surface to create the visible flash. This theoretical prediction was spectacularly confirmed in February of 1987, when detectors on Earth registered a sudden, precious burst. For a span of just 13 seconds, instruments in Japan and the United States captured 24 of these elusive messengers from a supernova in the Large Magellanic Cloud. This was not a vast number, but in the world of neutrino physics, it was a bonanza. Each interaction was a direct telegram from the heart of a stellar collapse, confirming decades of theory about how stars die. This event marked the birth of extrasolar neutrino astronomy, proving we could observe the universe using something other than light. Because neutrinos interact so weakly with matter, they escape the chaotic inferno of the collapsing core almost instantly, offering an unblemished, real-time view of the explosion's engine. By studying the energy and timing of these particles, physicists could test fundamental properties of the neutrinos themselves and refine our understanding of the violent dynamics at play. This has paved the way for a new early warning system for stellar death. Networks of detectors around the globe, collectively known as the Supernova Early Warning System, or SNUS, are now on constant watch. If a star in our own galaxy collapses, this network will send out an alert the moment the neutrino pulse arrives, giving astronomers precious hours to point their telescopes at the exact patch of sky before the first light appears. A future nearby galactic supernova would deliver not just 24 neutrinos, but hundreds of thousands of detections. Such a rich data stream would allow scientists to finally determine the neutrino mass hierarchy, the precise ordering of their tiny masses, and could even reveal new physics beyond the standard model. The faint ping of 24 particles from a distant star redefined these phantoms as crucial cosmic messengers, opening a window into the most hidden processes of stellar death. What other invisible, high-energy particles are constantly raining down upon our planet, carrying secrets from the most violent corners of the cosmos? These ghostly messengers from dying stars are joined by a far more aggressive rain of particles from across the cosmos. A single proton can be accelerated to energies millions of times greater than anything produced in the Large Hadron Collider, carrying the force of a professionally pitched baseball compressed into a single subatomic speck. These are cosmic rays, a relentless, invisible hail that has been bombarding our planet since its formation. Their discovery dates back to 1912, when physicist Victor Hess took delicate electrometers high into the atmosphere in a balloon. He found that the level of ionizing radiation increased with altitude, proving its source was not the ground below, but from somewhere deep in space. We now know these are mostly protons and atomic nuclei stripped of their electrons and hurled across the galaxy and beyond at nearly the speed of light. The most extreme among them, ultra-high-energy cosmic rays, possess energies beyond 10 to the power of 20 electron volts. A single particle like this carries the kinetic energy of a falling brick, all packed into a proton smaller than an atom. Their origins are one of the greatest mysteries in astrophysics. What natural particle accelerator in the universe is powerful enough to launch them? The prime suspects are the most violent objects we know, active galactic nuclei, where supermassive black holes devour matter and spew out colossal jets of plasma, could act as cosmic railguns. The shockwaves from supernova remnants, expanding for thousands of years, might also gradually boost particles to these incredible speeds through a process called Fermi acceleration, where they ricochet back and forth across a magnetic shock front like a ping-pong ball, gaining a little energy with each bounce. We cannot detect these primary particles directly as they shatter apart in the upper atmosphere. When a high-energy cosmic ray strikes an air molecule, it triggers a cascading avalanche of secondary particles, an extensive air shower that can spread over many square kilometers by the time it reaches the ground. Giant observatories like the Pierre Auger Observatory in Argentina use thousands of water-filled detectors spread across 3,000 square kilometers to catch the faint glow of these showers, while telescopes watch for the ultraviolet fluorescence they excite in the air. This invisible rain has been a surprising font of discovery. It was in the study of cosmic rays that the first antimatter particle, the positron, was found, along with the muon, a heavy, unstable cousin of the electron whose discovery led a physicist to famously exclaim, "Who ordered that?" Cosmic rays are more than just astronomical curiosities. They constantly irradiate our planet, contributing to background radiation and potentially influencing cloud formation and even genetic mutation over evolutionary timescales. They represent a fundamental thread in the ecology of our galaxy, transferring immense energy and influencing the dynamics of the interstellar medium. How do we capture the light from the universe's own natural particle accelerators to pinpoint their exact sources? A single, fleeting flash in the gamma-ray sky can outshine every star in the observable universe combined. These are gamma-ray bursts, the most powerful explosions since the Big Bang itself, discovered by accident in the late 1960s by Vela satellites, which were designed to monitor for nuclear tests. These bursts presented an immediate cosmic puzzle. They appeared from random directions in the sky, lasted from mere milliseconds to several minutes, and then vanished without a trace. For decades, their origins were one of astronomy's greatest enigmas. We now know these cataclysms come in two distinct varieties, each with a terrifyingly violent birth. Long gamma-ray bursts lasting more than 2 seconds are the death cries of the most massive stars in the universe. When such a star collapses, it does not just trigger a supernova, it produces a hypernova. The core does not form a neutron star, but collapses directly into a black hole. As matter swirls into the newborn singularity at near light speed, it launches two ultra-relativistic jets like cosmic blowtorches directly along its poles. If one of those jets is pointed at Earth, we see the concentrated energy of the entire stellar collapse focused into a narrow beam as a brilliant gamma-ray flash. The shorter bursts, lasting less than 2 seconds, have an equally dramatic origin. They are the signature of two ultra-dense objects, like neutron stars or a neutron star and a black hole, finally merging after a billion-year spiral. Their collision also forges a new black hole and sprays out a jet of material, creating a similar, if briefer, flash of gamma rays. The energy released in just a few seconds during either event is staggering. It equals the total energy our Sun will radiate over its entire 10 billion-year lifespan. Following the initial flash is an afterglow that fades across the electromagnetic spectrum, from X-rays to radio waves. This afterglow is our key to understanding the burst. Satellites like Swift and Fermi instantly pinpoint the location of a new burst and alert ground-based telescopes, which swing into action to capture the fading light. By analyzing this afterglow, astronomers can identify the host galaxy, measure its distance, and confirm the theoretical models. These cosmic beacons do more than just signal stellar death. Because they are so phenomenally bright, we can see them from the very edge of the observable universe. The light from the most distant gamma-ray bursts has been traveling for over 13 billion years, offering us a direct probe into the era of the first stars and galaxies. They act as searchlights, illuminating the ancient gas along their path and allowing us to study the chemical composition of the infant cosmos. Furthermore, the physics within these relativistic jets pushes matter to its absolute limits, creating conditions of intense magnetic fields and gravity that we can never hope to replicate on Earth. They are natural laboratories for testing the strongest predictions of Einstein's theory of relativity. What cosmic engine can possibly launch and focus such a devastatingly powerful jet, converting the gravitational death of a star into a focused beam that can be seen across the universe? These cosmic blowtorches are not confined to stellar deaths. At the heart of many galaxies, including our own Milky Way, a supermassive black hole can ignite the most powerful and persistent engines in the universe. From these gravitational monsters erupt relativistic jets, narrow beams of superheated plasma that scream across space at over 99% of the speed of light. They can stretch for hundreds of thousands of light years, far beyond the boundaries of their host galaxy, like impossibly long spears hurled into the cosmic dark. The power source is the black hole's insatiable appetite. As stars and gas clouds are pulled into the abyss, they do not fall straight in. Instead, they form a swirling, frantic disk of material called an accretion disk, heated to millions of degrees by friction and gravitational compression. Some of this doomed matter, along with immense magnetic fields twisted into a tight coil by the black hole's spin, is funneled away from the poles and launched outward in two opposing, tightly focused jets. This entire system is known as an active galactic nucleus, and its jets are a masterclass in cosmic efficiency, converting the raw gravitational energy of infalling matter into directed kinetic energy with staggering effectiveness. We can observe these jets across the entire electromagnetic spectrum. Radio telescopes, especially networks like the Very Long Baseline Array, act as a single Earth-sized instrument, resolving details finer than a light year across in a distant galaxy. These images reveal the jet structure in stunning detail, showing bright knots where internal shocks accelerate particles to nearly the speed of light, causing them to shine in synchrotron radiation. The impact of these jets on their surroundings is profound. When they plow into the tenuous gas that exists between galaxies in a cluster, they inject immense energy, heating the gas and preventing it from cooling and collapsing to form new stars. This feedback process is a crucial yet subtle force in galaxy evolution, effectively putting a cap on how large a galaxy can grow. It reveals a self-regulating cosmic ecosystem, where the black hole at the center can dictate the fate of the entire galaxy that surrounds it. Even within our own galaxy, we see smaller-scale versions of this phenomenon in microquasars, where a stellar mass black hole feeds on a companion star and produces miniature but equally fascinating jets. How can the immense gravity of a black hole, a force that traps light, simultaneously power the most luminous outbursts in the cosmos? The answer lies in the chaotic frontier just outside the event horizon, where the laws of gravity and quantum mechanics engage in their most direct conflict. A black hole is not a one-way street to nowhere. It glows, and in doing so, it slowly dissolves. This startling idea emerged from Stephen Hawking's mind in 1974, when he performed a calculation that merged the laws of the very large with the laws of the very small. He asked what would happen if quantum mechanics met the intense gravity at a black hole's event horizon. The result was Hawking radiation. The quantum vacuum of space is not truly empty. It is a seething foam of virtual particles, pairs of matter and antimatter that constantly flicker into existence and then annihilate each other almost instantly. Normally, this dance leaves no trace, but at the edge of a black hole, the gravitational pull is so immense that it can tear these pairs apart. One particle falls past the event horizon, forever lost to the outside universe, while its twin escapes, radiated away into space. To an outside observer, it appears the black hole has just emitted a particle. This process is not free. The energy for creating the escaped particle comes from the black hole's own mass. Slowly, over epochs of time that dwarf the current age of the universe, a black hole loses mass through this quantum leak, shrinking until it potentially vanishes entirely. Hawking's work redefined black holes forever. They are not cold, eternal prisons. They have a temperature, a faint heat proportional to their surface gravity, and they possess entropy, a measure of their internal disorder. This made them thermodynamic objects, subject to the same laws of heat and energy as a steaming cup of coffee, only trillions of times colder. This brilliant unification, however, created one of the most vexing problems in modern physics: the black hole information paradox. In quantum mechanics, information is never truly lost. If you burn a book, in principle, you could recover its information from the smoke and ashes. But if an object falls into a black hole, and that black hole then evaporates into a featureless bath of Hawking radiation, what happened to the information it contained? Is it truly erased from the universe, violating a foundational quantum rule? This paradox forces a direct confrontation between general relativity and quantum mechanics, and its resolution may require a theory of quantum gravity. While we have not yet directly observed Hawking radiation from an astrophysical black hole, its influence is profound. It has inspired laboratory experiments that create analog event horizons in fluids and other materials, allowing us to study these quantum gravitational effects up close. It suggests that spacetime itself may be built from more fundamental quantum bits, and that a black hole's surface area might literally count its internal states. If a single black hole can be described by quantum rules and thermodynamics, what happens when we apply that same quantum thinking to the cosmos as a whole? The next step pushes this idea to its ultimate limit, suggesting our universe is just one page in an infinite cosmic library. Our universe might be just one page in an infinite cosmic library. This is the staggering idea of the multiverse, a vast ensemble of universes, each with its own unique set of physical laws and constants. Ours with its precisely tuned numbers that allow for galaxies, stars, and life, could simply be one bubble in a sprawling cosmic foam where the rules are different everywhere. This concept does not come from science fiction, but emerges naturally from the edges of our most successful physical theories. The theory of cosmic inflation suggests that the rapid expansion of spacetime did not happen just once, but is eternal, continually spawning new pocket universes in an ever-expanding meta-universe. String theory proposes a landscape of perhaps 10 to the power of 500 possible vacuum states, each corresponding to a universe with a different physics. Even the many worlds interpretation of quantum mechanics, which avoids the spooky collapse of the wave function, posits that every quantum decision branches off a new, equally real universe. This radical idea offers a potential explanation for the most profound mystery in cosmology, the fine-tuning problem. Why are the fundamental constants, like the strength of gravity or the mass of an electron, so perfectly calibrated to allow for complexity and life? If there are an infinite number of universes, then it is no surprise we find ourselves in one of the rare habitable ones, simply because we could not exist anywhere else. This line of reasoning is known as the Anthropic principle, yet the multiverse remains deeply controversial. How can we ever test for the existence of something forever beyond our cosmic horizon? Critics argue that if a theory predicts everything, it ultimately explains nothing, pushing it beyond the bounds of empirical science into the realm of metaphysics. Proponents counter that it is the natural, almost inevitable, extension of our current best theories, and that its indirect evidence may one day be found imprinted in the patterns of the cosmic microwave background, or through a deeper understanding of quantum gravity. This idea forces us to confront the very nature of reality and our place within it. Are we the unlikely winners of a cosmic lottery, or is our universe the product of a deeper yet unknown law? The multiverse challenges the Copernican principle to its ultimate extreme, suggesting that not only are we not at the center of the universe, but our entire universe may not be central to anything at all. It expands the canvas of reality to its absolute limit, pushing cosmology and philosophy into a profound and dizzying union. The precise calibration of the universe feels less like a random accident and more like a carefully set stage. Why do the fundamental constants, from the force of gravity to the mass of an electron, possess just the right values to allow for the formation of stars, planets, and ultimately, conscious life. This profound puzzle is the heart of the anthropic principle, the final mind-bending event that redefines our place in the cosmic order. In its simplest, weak form, the principle makes a seemingly obvious statement. We can only observe a universe whose laws are compatible with our existence as observers. It is a selection effect, like a fisherman only being able to catch fish from a lake that actually contains fish. The strong form of the principle, however, takes a far more radical step. It proposes that the laws and constants of the universe must be such that they allow life to arise at some point. Here, the existence of observers is not a lucky outcome, but a necessary feature that somehow constrains the physics itself. This idea, formally articulated by physicist Brandon Carter in the 1970s, forces a dramatic shift in perspective. It bridges the cold equations of physics with deep philosophical questions about purpose and design. The most compelling evidence for fine-tuning lies in the numbers themselves. If the force that binds atomic nuclei were just a few % weaker, only hydrogen would exist. If it were slightly stronger, all the hydrogen would have burned into helium in the early universe, leaving no fuel for stars like our Sun. The cosmological constant, which drives the acceleration of the universe, is fine-tuned to an accuracy of 1 part in 10 to the power of 120. A value only slightly larger would have blown the cosmos apart before any structure could form. A value slightly smaller would have caused it to collapse back on itself instantly. Our universe exists in a breathtakingly narrow window of viability. So how do we explain this incredible luck? The anthropic principle finds its most powerful, though controversial, partner in the concept of the multiverse. If an infinite or near-infinite number of universes exist, each with its own random set of physical constants, then it is no surprise that we find ourselves in one of the rare habitable ones. We are not the purpose of the cosmos, but simply the lucky inhabitants of a cosmic oasis in a vast desert of sterile realities. This does not make our universe any less special to us, but it recontextualizes its specialness from a planned event to a statistical inevitability in a grander ensemble. This framework transforms the question from why the universe is fit for life to a more humbling inquiry. Why are we here to notice it? It challenges the Copernican principle to its ultimate conclusion, suggesting that while our planet is not the center of the universe, our ability to observe it is the very reason we perceive its laws in the first place. The anthropic principle, therefore, is not an answer but a new way of framing the question. It connects the quantum flutter of virtual particles to the vast expanse of cosmic inflation, and ties the fate of dying stars directly to the existence of conscious minds. From the faint echo of the Big Bang to the ghostly whisper of dark matter, from the spooky connection of entangled particles to the evaporating glow of black holes, these 25 events collectively reveal a reality far stranger and more wonderful than we ever imagined. They show us that the laws of nature are not rigid, eternal decrees, but a dynamic, evolving story. They are a narrative of breaking symmetries, of cosmic accidents, and of a fundamental interconnectedness that binds the quantum realm to the cosmic web. Our journey through these redefined laws leaves us with a universe that is less a cold, mechanical clock and more a living, breathing puzzle. One that we are only just beginning to learn how to read. These 25 events are not isolated curiosities. They weave a single, breathtaking tapestry of reality, from the spooky quantum connections that bind particles across galaxies to the dark energy, relentlessly pushing the cosmos apart. Each discovery, from the faint hiss of the cosmic microwave background to the violent chirp of colliding black holes, chipped away at our classical intuitions, revealing a universe built not on certainty, but on probability and broken symmetries. The ghostly presence of dark matter sculpts the galaxies, while the fleeting existence of virtual particles dictates the fate of black holes. We have learned that the act of observation crystallizes reality from a fog of possibilities, and that empty space itself possesses a vibrant energy. This grand narrative exposes the fundamental clash between our two most powerful theories. Einstein's graceful space-time curvature of general relativity governs the cosmos on its largest scales, while the frantic, probabilistic rules of quantum mechanics dictate the behavior of the very small. Their stubborn refusal to unite on common ground, especially at the singularity of a black hole or the moment of the Big Bang, is the greatest unsolved problem in physics. Yet, this very tension fuels the quest for a theory of everything, inspiring profound ideas like string theory, which suggests that the fundamental constituents of reality are not points, but unimaginably tiny, vibrating loops. The journey through these events teaches us a humbling lesson about the scientific process itself. The detection of gravitational waves a century after their prediction, and the hunt for the Higgs boson, show the immense power of human curiosity married with technological ingenuity. We predict, we build, we observe, and the universe answers, often in ways we never anticipated. At the same time, the enduring mysteries of dark matter and the matter-antimatter asymmetry are stark reminders that our knowledge is still a tiny island in a vast ocean of the unknown. They are not failures, but beacons guiding the next generation of explorers. The overarching lesson is that the laws of nature are not rigid, eternal commandments carved in stone. They are a dynamic, evolving story, a narrative we are actively unraveling. Every answer peels back a layer to reveal a deeper, more fascinating question. Our cosmic journey from the first nanosecond to the far future is a single, connected epic, and we are both its audience and its authors, forever redefining the rules of existence through the simple, powerful act of looking up and asking why. Our journey through these 25 cosmic revelations paints a universe of breathtaking wonder and profound mystery. From the faint whisper of the Big Bang's afterglow to the quantum evaporation of black holes, each discovery has systematically dismantled our classical view of reality. We have seen that the cosmos is not a cold, predictable machine, but a vibrant, evolving story written in probabilities and broken symmetries. This ongoing scientific endeavor thrives on overturning old certainties, reminding us that our understanding is always provisional, always reaching for the next horizon. The great astronomer Carl Sagan perfectly captured this spirit of exploration when he said, "Somewhere, something incredible is waiting to be known." These insights do more than just fill textbooks. They offer a profound sense of humility, placing our tiny, curious species within a vast cosmic tapestry woven from dark matter, stitched with gravitational waves and driven by dark energy. We are both the audience and the authors of this grand narrative, forever asking questions that push the boundaries of the possible. So we turn the final reflection over to you. Which of these events reshaped your own sense of reality the most? Was it the spooky connection of quantum entanglement, or the invisible hand of dark matter holding galaxies together? Share your thoughts in the comments below. And if you enjoyed this voyage through the laws of nature, subscribe for more journeys to the edge of understanding. Remember, the rules of the cosmos are not commandments carved in stone. They are written in the stars, waiting for the next curious mind to read them, to challenge them, and to bend them even further.